Kirchoff's rules, or sometimes known as Kirchoff's laws depending on the text you're using. Up until this point, we've been analyzing fairly simple circuits. We would combine resistors either in series or parallel, or maybe both at the same time, but not very many of them. This works for simple circuits, but in order to analyze more complex circuits where perhaps you have multiple batteries or multiple different configurations of the resistors, we need to use Kirchoff's rules. These are based on the laws of conservation of charge and the conservation of energy. Kirchoff's first rule, or the junction rule, is based on the law of conservation of charge. It states that at any junction point, which we represent here by a dot, that's where two pieces of the circuit come together and leave as one, the sum of all the currents entering the junction point must equal the sum of all the currents exiting the junction. So whatever charges are coming in here, they all have to leave together. So for example, I1 plus I2 has to equal I3. Kirchoff's second rule, or the loop rule, is based on the law of conservation of energy. It states that the sum of all changes in potential, electric potential, around any closed path must equal zero. So if we have a closed path like this, we have voltage supplied by the battery. And now what is voltage again? It's always good to remember that. That's basically defined as potential energy per charge. So whatever energy is given to the charge here, as it goes around this loop, it transfers that energy into thermal energy or work if you're running a vacuum cleaner, different types of energy. And by the time it gets back here, it has transferred all of the energy it was given. So the sum of the positive potential here and the negative potentials here has to equal zero. For the clockwise path shown below, which is the same direction as a conventional current is, okay, so we're going to draw the lines here for the conventional current. When we have this configuration, we will assign a positive value to the potential and negative values to the resistors, to the voltage dropped in the resistors, because the path we chose is in the same direction. Now if we chose the other path, if we went around counterclockwise, we reverse the sign configuration. This will become more clear as we work through a problem next. So if we're going this way in our path, we will have a negative voltage, and this would then be a positive voltage drop, and so would this, because the path chosen is opposite the assumed current flow. Don't worry too much about that right now. In either case, you'll get the same answer. The sum of the voltages equals zero. Energy is conserved. No new energy is brought into the system and no energy is lost.